Greetings to all the viewers. I hope I find you well. I'm doing great. I'm back with another presentation. Today I will be presenting on question number 5 of November 2023 Physical Sciences Paper 2. This is a reaction rates question, which in this paper had 19 marks. 19 marks, it's a lot out of 150. So if you master this topic, you know that you will be having a lot of marks from this question. All right, so the question reads, the reaction between excess hydrochloric acid and sodium thiosulfate is used to investigate factors that influence reaction rate. Okay, so here excess is even written in capital letters. Okay, so if one reactant is in excess, the other reactant becomes the limiting reagent. So sodium thiosulfate is the limiting reagent of this reaction. It is the one that is going to determine the amount of the products that will be formed in the reaction. It will also be the reactant that will be completely used up in the reaction. Okay, so it is very important that every time you are given a reaction, you are able to determine which one is the limiting reagent. And in most cases, they will tell you which one is in excess. So the other one becomes the limiting reagent, the one that is not in excess. Okay, so here the examiner just told us that and the experiment is all about investigating the factors that influence reaction rate and did not tell us which factor is under investigation. So by analyzing the results given here, we must be able to tell which factor was under investigation. The factor under investigation will be the independent variable. Okay, so it's as easy as that. Reaction rate is always the dependent variable, and the factor under investigation is the independent variable. Okay, so we are going to analyze and see what factor is under investigation. Okay, so the concentration of HCl, hydrochloric acid, used is 1 mole per cubic decimeters, and then same amount of HCl is used. So this is actually a control variable, same amount of HCl being used. Okay, then time taken for the cross on the paper under the flask to become invisible is measured. Okay, so this is an experiment which is also known as the cross disappearance experiment, whereby a flask with your sodium thiosulfate and hydrochloric acid is placed on top of a paper marked with a cross. Okay, so the moment you just add hydrochloric acid into the conical flask, the reaction will start to take place, a reaction which produces sulfur. Sulfur is yellowish in color. So as the intensity of the yellowish color increases, the cross will be covered or obscured to the extent that to some point you will not be able to see the cross. So the moment you will no longer see the cross, you just stop the stopwatch and record the time that it takes for the cross to completely disappear. Okay, so that is the experiment or the investigation. So here the experiment consisted of, or the investigation consisted of 3 runs. Runs are just experiments. The examiner decided to just use an unfamiliar term, run, instead of experiment. So we have run 1, 2, and 3, or experiment 1, 2, and 3. Right, so in experiment 1, 50 cubic centimeters of sodium thiosulfate are used, and then in experiment 2, 40, experiment 3, 30. Then in experiment 1, no water was added, meaning that the sodium thiosulfate was not diluted. Experiment 2, it was diluted with 10 cubic centimeters to make a total of 50. In experiment 3, the sodium thiosulfate was diluted with 20 cubic centimeters of water to make up a total of 50 cubic centimeters. So by adding water, the sodium thiosulfate is becoming more and more diluted. So the factor under investigation here therefore becomes concentration, because by adding water, the concentration is being changed. So whatever factor or whatever quantity is being changed becomes the independent variable. Okay, so our question number 5.1, the first question, is simply defining the term reaction rate. Right, if you know the definition of reaction rate, then defining reaction rate becomes so simple, because the definition of reaction rate comes from the formula for calculating reaction rate. So let me just write here the formula for calculating reaction rate. Reaction rate equals delta, meaning change in square bracket, means concentration of reactants or products. Okay, this is products divided by delta T. Okay, so in words, we are just going to put this in words. Reaction rate 5.1 becomes a change in concentration of reactants or products per unit time. That is the definition of reaction rate. That is just 2 marks for free. Okay, 5.2, write down the independent variable. Like I highlighted before, that the independent variable is always the factor under investigation. So here we've just determined that the factor under investigation is concentration, because here we do have concentration of sodium thiosulfate being changed or being manipulated by adding some water to dilute the sodium thiosulfate. So our independent variable there is concentration. Okay, so 5.2, our answer there is concentration. We move on to question 5.3. Okay, calculate the value of P in the table. We've got various formulae that we can use here. We can use the ratio method, whereby here the 50 cubic centimeters, the undiluted volume, has got a concentration of 0.13. Okay, then the 30 must have a lower concentration. So it's a simple ratio. The undiluted must have a higher concentration, the diluted a lower concentration. So we are simply going to say 5.3, 50 cubic centimeters is to 0.13. Okay, that is the concentration of this undiluted. Then the 30 is to x. Then we cross multiply. It becomes 50 by 30, 50 by x, 50x equals 30 times 0.13. Okay, our x will be, we divide both sides by 50. Okay, that will be 30 times 0.13 divided by 50. Right, I'm getting on my calculator here 0.078. 0.078. Okay, alternatively we can use the dilution formula. C1 V1 equals C2 V2. So C1 is the concentration of the undiluted solution. So here we are taking the 0.13 is the undiluted solution, this 50 cubic centimeter without any water added to it. So 0.13 multiplied by V is the volume that is going to be diluted. So in this case, the volume that is going to be diluted is this 30 multiplied by 30. 30 is going to be diluted. C2 is the new concentration after dilution. So after dilution, we are going to get concentration P, the one that we've just been requested to calculate, multiply by, this is the new volume after dilution. So after diluting the 30 cubic centimeters with 20, the total volume of the solution will be 50. So it's P multiplied by 50. Okay, it will just be the same as this 50x, here is P by 50, then 0.13 times 30, 30 by 0.13. So dividing both sides by 50 will also give us our P as 0.078. I'll just use capital letter M for moles per cubic decimeter. So this is how we simply calculate the value of P in question 5.3. All right, let us move on to question 5.4. Right, when 0.21 grams of sulfur has been formed in run 1, the cross becomes invisible. Okay, calculate the average reaction rate with respect to sodium thiosulfate. Sodium thiosulfate, which is a reactant. Okay, in grams per second. So the unit that the examiner requires you to calculate the answer in determines the formula that you are going to use. So here, if the unit is supposed to be grams per second, it means the formula for reaction rate is going to be 5.4 reaction rate is equal to minus change in mass, delta M, that is change in mass, over change in time. Okay, this will be negative, I'll explain that, negative M final minus M initial over delta T. Right, here I've put negative because we are calculating the reaction rate with respect to the sodium thiosulfate, which is a reactant. When reactants are reacting, their amounts, whether it's the mass or concentration, decreases. So that decrease is actually a negative change. If it was calculating the rate of reaction with respect to a product, it was going to be a positive here, because products change positively. At the beginning of the reaction, there won't be anything of the product, but as the reaction progresses, the amount of the product will be increasing. That's a positive change. But with a reactant, the change is negative, hence a negative sign there. Okay, right. So we now need to know the values of the final mass and the initial mass. Okay, Time is not a problem because we are asked to calculate for run 1 where time is 20.4. Okay, so here we need to know the mass of sodium thiosulfate that was responsible for the formation of the 0.21 grams of sulfur. Okay, so from this equation here, we have a ratio of 1:1. So if we can calculate the number of moles of sulfur, it will be the same as the number of sodium thiosulfate that would have reacted. Okay, so with that number of moles, we can calculate the mass of sodium thiosulfate that reacted or that was initially present. So let us first calculate the mass of sulfur, the number of moles of sulfur. Okay, so it's going to be N sulfur equals the mass over molar mass. Okay, mass there were given as 0.21. Let me just verify. 0.21 grams, yes, divided by the mass of sulfur, 32. Okay, let me check there with my calculator. 0.21 divided by 32. Okay, 0.00656 moles. Okay, so this is also the number of moles of sodium thiosulfate because the ratio from the balanced equation of sodium thiosulfate to sulfur is 1:1. Okay, so the mass of sodium thiosulfate becomes, so this is Na2S2SO3 equals mass over the molar mass. So we said number of moles here of sodium thiosulfate is the same as the number of moles of sulfur because of the ratio 1:1. Na2SO3 is to sulfur, the ratio is 1:1. Okay, so I'm going to say 0.00656 is equal to mass divided by the molar mass of sodium thiosulfate will be 23 times 2 plus sulfur 32 times 2 plus the mass of oxygen 16 times 3. Okay, right, I'm going to use my calculator here. 23 times 2 plus 32 plus 2 plus 16 times 3. Okay, this is giving me 128. So 128 multiplied by 0.00656. Okay, it's giving me a mass of 0.8396 grams. Okay, let me just check again. 23 times 2 plus 32 times 2 plus 16 times 3. Okay, 158 times 0.00656 0.00656. Okay, right. I had actually made a mistake in punching my calculator there. So this is simplifying to 1.03648 grams. Okay, so this is the mass of sodium thiosulfate that produces the 0.21 grams of sulfur. Okay, that will be the initial mass available. Okay, so to calculate rate of reaction, I'm going to say minus final mass. It will be 0 because all the 1.03645 grams would have reacted. Okay, it's going to completely react because sodium thiosulfate is the limiting reagent. Okay, so minus, initially there will be 1.03648 divided by the time that is given for run 1, 20.4. 20.4. Okay, let me check what will this simplify to. 1.03648 divided by 20.4. Okay, the rate will be 0.05 grams per second. Okay, that is our final answer. This is change in mass in grams, change in time in seconds, hence our unit is grams per second. Okay, so we are done with 5.4. Let us move on to the next question. Another investigation is performed at different temperatures. Sketch the Maxwell-Boltzmann distribution curve or energy distribution curve for the reaction at 20 degrees Celsius. Okay, at 20 degrees Celsius, label this curve as A. Then on the same set of axes, draw the curve that will be obtained at 35 degrees Celsius. 4 marks. That is quite easy question. 4 marks that are easy to get. All right, so 5.5. 5.5. So Maxwell-Boltzmann energy distribution curve, it has the y-axis and the x-axis. On the x-axis there is kinetic energy. On the y-axis, number of particles. Number of particles. All right, our axis start from 0. All right, so I'm going to start with the graph for a temperature of 20 degrees Celsius. Okay, so for 20 degrees Celsius, okay, so for normal distribution curve. All right, then here we have our activation energy, EA. Okay, I'm going to shade the region that represents particles with sufficient kinetic energy. So all these particles are the particles that can collide and react because they have kinetic energy equal to or greater than the activation energy. Okay, so this is our A, which represents a temperature of 20 degrees Celsius. Okay, so let me label it A in brackets 20 degrees Celsius. Right, then the second graph is for 35 degrees Celsius. Okay, So for 35 degrees Celsius, there's going to be an increase in the average kinetic energy. Right, so average kinetic energy from the graph here is just the kinetic energy that corresponds to the turning point of the graph. So here, that is where our average kinetic energy is. Right, increasing temperature will make the graph become skewed to the right. So we are going to have this graph a bit lower than that of 20 degrees Celsius, but on this side it will be now higher. Okay, turning point here is somewhere at this point. So you can see that at a higher temperature, so this is now B 35 degrees Celsius. At a higher temperature, the average kinetic energy is now greater than the average kinetic energy at a lower temperature. This is the average kinetic energy at a lower temperature, average kinetic energy at a higher temperature. So that's the effect of temperature. It increases the average kinetic energy. Okay, our activation energy does not change. It remains the same. Okay, for both temperature of 35 degrees Celsius and 20 degrees Celsius. So at that higher temperature, the number of particles with sufficient kinetic energy will increase. It will be these particles plus these additional particles. So you can see here that by increasing the temperature, we now have more particles with sufficient kinetic energy. This whole area is representing the number of particles with sufficient kinetic energy at a higher temperature. But at a lower temperature, we have few particles with sufficient kinetic energy. Okay, so that is the Maxwell-Boltzmann energy distribution curve. Question 5.5. Then you get your 4 marks. Let's move on to 5.6. Explain the effect of temperature on reaction rate in terms of the collision theory. 5.6. Okay, this is one question, very easy to answer, but I've realized that learners like to write a lot of things here. They write times you find learners writing a passage, unfortunately in some cases without any point. So in physical sciences, what matters most are your facts and points, not the quantity. We consider the quality. So your first point here, under the effect of temperature, it is to be when temperature is increased, the average kinetic energy of the particles increases. When temperature is increased, the average kinetic energy of reactant particles increase. So the key point here is increase in the average kinetic energy. Second point, number of particles with sufficient kinetic energy increases, like I was explaining here on the Maxwell-Boltzmann energy distribution curve, that initially when temperature is increased, average kinetic energy increases. You see here at a lower temperature, this is the average kinetic energy. At a higher temperature, the average kinetic energy is now increased. Okay, that's where the first point is coming from, an increase in average kinetic energy due to the increase in temperature. Then second point, number of particles with sufficient kinetic energy increases. So here at lower temperature, this was just the number of particles, but at a higher temperature, the number of particles with sufficient kinetic energy increases. And when we say sufficient kinetic energy, it simply means EK greater than or equal to EA. That is what we mean by sufficient kinetic energy. Then your last point will be the frequency of effective collisions increases. A point which you can also write is the number of effective collisions per unit time increases. So I like this shorter one. The frequency of effective collisions increases. Okay, that is the three main points that will give you your 4 marks. Instead of just writing a paragraph without any quality, you just have to go for the points, whereby you know that for this point I'm getting my mark or my marks. So as simple as that. Okay, so I think this was the last question 5.6. Okay, so we have come to the end. Okay, that was the question number 5 of the November 2023 paper 2. It's not a very difficult question, it's quite simple question. First part normally is all about it's an experimental question whereby they will be testing you to check if you know how to determine the dependent variable, the independent variable, even the control variables. Then from there, calculating the reaction rate. That's the question with the highest number of marks. Yes, you can see there's 5 marks there of calculating the reaction rate. But if you know what you're doing with thorough revision, the 5 marks or more can actually be very easy to obtain. And in most cases, the last part normally is about the Maxwell-Boltzmann energy distribution curve, as well as the explaining the factors using the collision theory. Right, I hope you enjoyed the presentation. Next time I'll be back with another past examination paper. I'm just going to focus on the November, May, June, November, May, June. So right now I've done November 2023. I'll also look for the June 2023. So that you have an understanding of the typical examination question, because in some cases you find that the preparatory papers won't be that challenging. So I prefer to present these final papers. They will give you a very, very good practice. Right, from me for now, it's bye-bye.